Yeah, that's what's all over my notes.
Okay, so you have your exams back, and I'll spend a little bit of class time talking about the exams. I won't spend a ton of time, but I will also scan the key to it, and I'll post that out on D2L, so then you can take your test at your leisure and compare it to the key, and then start asking me questions by email or bring them to class or whatever. Question so-and-so on the test. I don't understand why you do it that way. Right? I guess I won't worry about being able to write on that. The first problem with the four assumptions, I was surprised actually there were several people that didn't get that or didn't get all of the four, because I think I hinted at that was going to be a question on there. What are the four? Constant variance.
Individual, independent.
Okay, all individual points should be independent.
Normally distributed residuals.
The residuals, and therefore the y variable, should be normally distributed. We'll talk today more about this, but it does not specify that the x variable has to be normally distributed. It's only the y variable, and through the y variable then the residuals. But okay, and then one more.
That is a linear function.
That the mean value of y for any given x, as x changes, that should be a linear function. So, well, on my key I just wrote linearity. That's the linearity assumption. All right. On number 2, you had one like this on the practice exam, but the p-value was in between 0.01 and 0.05. This one I made bigger than 0.05, which changed the answer to both a 99% and a 95% confidence interval would contain the number 4. You would fail to reject that null hypothesis. Okay? So then the first problem where you really had to work was this one, which was a chi-square test on the severity of illness, whether you get echinacea as a supplement or you get placebo as a supplement. And this went really well for most people, so I don't know that I need to say too much about it. This question about, for the echinacea group, find the conditional distribution of severity ratings. What I got, people that missed that did column percents instead of row percents. Right? So what's the tip-off? How do you know which to do? Conditional distribution of severity ratings. So the of tells you, I want the distribution of how are people distributed across severity. So for the echinacea group, so you're looking only at the echinacea group. So you know you're doing row percents. So those should all be 153 divided by 329, 128 divided by 329, and so on. Okay, then a chi-square test is what you do. You do it using your calculator, or if you didn't remember how to do it, then you could do each cell with observed minus expected quantity squared over expected, and then sum them all up. I don't think anybody had to resort to that. Mostly what I got was just what looked like the output from your calculator, right? Which is fine. So the test statistic should have been 2.506. And the p-value 0.2857. So 2857, is that a big p-value or a small p-value?
Big.
That's a big p-value. And big p-values tell you what?
Fail to reject the null.
To fail to reject the null. There's still a few of you that are saying that part right, but then in words, you're reversing it. Like, I fail to reject, therefore there is sufficient evidence of an association. No, the null is there's no association. So if you fail to reject the null, then you're saying I don't have evidence. Right? Okay. This problem on the goodness of fit, this was very commonly missed. Leanna, I'll probably have to have you tell me, how do I write on the screen again?
writing all that.
And do I do that from Active Inspire? So, don't remember? Come on, neither do I.
Well, you might be able to actually from that first menu when you open it.
The other window?
So click on the
bottom thing again, where you just click.
This thing?
Down,
Bottom.
down, there.
Yeah, you're
On
right.
Active Inspire,
Okay.
and then the right, that.
Oh, this. Okay, gotcha.
So you can just click annotate over the desktop,
There we go.
and then you can close the page browser. And then you can write on that. You'll just have to erase it before you scroll.
Yeah, and that's fine. So this number 5, distribution of test scores on a standardized test, it tells you that they are normally distributed. So the common mistake here was, oh, you gave me 4 regions, so I should have 25% in each of those 4 regions. When you do a goodness of fit test, you have to think, well, what would I expect in those regions if it is normal? So you're testing the goodness of the fit of a normal distribution. Well, if you have a normal distribution, and it's got a mean of 78, so 78 would be there, and one standard deviation is 10 units, then that takes you to 68 and 88, which are used as boundaries, and the 78, right? So you've got, this is region 1, 2, 3, and 4. They don't look like they have the same percentage in each of those, do they? They're not 25% in each of those. So how much is in region 1? 16%. And what do you use to figure that out? Empirical rule. Now, some people used empirical rule, some people use normal CDF, and I actually use normal CDF on my key, which is not exactly 16%, it's 15.87 or something like that. So, but it's real close, right? So this would be, we'll go with the 16% in there, and then in here, between the 2 dotted lines, by the empirical rule, is how much percent? 32, so half of that's in 2 and half of that's in 3. So this would be 34%, 34%, and another 16%. Then you just take 16% of the 500 to get the answer. Which part am I doing? Right here. Assuming the data does, what would the expected count be for the first region less than 68? The expected count would be 0.16 times 500. Right? So how much is that? 80. And on my key, I think I have 79.33 because I used the 15.87% instead of 16. Either one got full credit. Okay, both of the next 2 questions. No, this question went great. This question went horrible. So let me clear that. How do I clear it all at once?
Spray bottle.
Spray bottle. I got to learn all this stuff. There we go. So, there you go. Okay. An investigator performs a linear regression analysis using one predictive variable. The residuals from the model are output to a data set, right? Then the correlation of these residuals and the predicted Y values, not the actual Y values, is computed. What will the value of this correlation be? And it was just, this was a thought process. I'm going to see if you have the insight into the data, right? And what I found was about 1/3 of you have the insight and 2/3 of you don't, which is okay. I didn't weight this very heavy. I think it only was worth 2 points. But so let's talk about it. Think about this. The predicted Y values, what does that represent? The predicted Y values. for a given x value, the predicted y value falls on the line, right? And remember the ANOVA table, where you have sum of squares due to regression and sum of squares due to error? And then those two added together give you what? Sum of squares total. So the total amount of variability in the y variable can be divided into what the model can explain and what the model cannot explain. The error, the residuals, are what the model cannot explain. So the predicted values are what the model can explain. So what do you think the correlation is between what the model can explain and what the model cannot explain? 0. There should be no correlation there, because anything that can be explained has been explained, and the residuals represent random noise, random error that we have no idea why this person was taller than what their shoe size would predict. Right? So this should be 0. And I can illustrate that for you pretty easily when we do a regression in Excel, and you click the box to say, give me the residuals. Then you can take that column of residuals and put it next to the column of predicted values, or actually they're already next to each other, and then just use the correlation function. Say, what's the correlation between these two? And it'll be 0. No matter what your data set you're dealing with, it'll be 0. Right. Okay, so then number 8, most people recognize that, yeah, there's a problem. It's not always that you knew what the right problem was, what the problem was. Well, this is a histogram of residuals, right? And what's the assumption that we talked about a minute ago for residuals? They should have what distribution? Normally distributed. So this has a normal curve over the top, but what the histogram of the residuals, it tells you that normality assumption is violated. Right? So I got other things that were wrong, but that's what the correct answer is. Keep doing that. Huh. Okay, number 9 is mean squared error, right? So this is sum of squared errors divided by the degrees of freedom for error. That's mean squared error. Right? So that's just the MSE from the ANOVA table. This problem, to get the equation of the line, you needed that one set of equations that the correlation coefficient, the slope, B1, is equal to the correlation coefficient times SY over SX. All 3 of these things you were given up in there. Right, so that turns out to be 14.863. And then B0, once you have the slope, how do you get the intercept? Okay, the mean of the y minus the slope times the mean of the x's. Right? So when you plug in, all those are given to you up there, so when you plug that in, you get a really weird value, which doesn't seem to make sense, but remember, it won't always make sense. Negative 28,517.5. So we're going to expect to get negative 28,000 tornadoes? How do you get negative tornadoes? Well, when is year 0? A long time ago, right? BC, AD. So when Christ was alive, they had negative 28,000. It doesn't make sense to extrapolate that far. Don't worry about that, right? So it's just y hat is 28,517.5 plus 14.863 x, and x is year, right? So give the interpretation, then that's how many tornadoes how many more tornadoes you expect every year. Every year we get about 15 more tornadoes than the year before. Interpretation, let's see, mean squared error. I gave you mean squared error and then asked you to do predicted value, standard error of predicted value, and the 95% prediction interval. So this will take a long time to do, so I'm not going to do everything, but predicted value should have been 1297.68. So y hat. And how do you get y hat? You plug 2006 into the equation. That's right. So the equation that I just had up here, your x is 2006. Just plug that in, and you should get 1,200. So just a hair under 1,300 tornadoes. And then the standard error. So I'll put the formula for the standard error of a predicted value up here, and then we'll quit on this one, and you can look up the right answer if you didn't get it. But you need SE, and then square root of 1 plus 1 over n plus, and then it's the value of x that you're interested in, 2006, minus the mean of the x's, right? Oh, I'm mixing numbers, but you understand what I'm doing? So this is x star, and this is x bar. Then on the bottom is n minus 1 times sx squared. What is s sub e? That's the root mean squared error, which is called the standard error of the estimate. So root mean squared error. So they told you what the mean squared error was. Take the square root of that number, and that's what goes in there. Okay? And then you get that standard error, and you get a t critical value, and then you just take your predicted value plus or minus the t critical value times the standard error. Okay? And if you had the right interval, then the answer to this was yes. The confidence or the prediction interval did contain 1117. It's actually a pretty wide interval, so it contained a lot of things. Is everybody done with this? Now this page was either you got almost everything or you didn't, right? So it's difficult to test this kind of a thing without having a problem where if you miss one thing, it trickles through the whole thing. But degrees of freedom, most people got that right. Total degrees of freedom is always 1 less than the sample size, and error is always 2 less than the sample size, as long as you have only one x variable in there. So 76, 77. Okay. And then how do you get the model sum of squares? By subtraction, right? The missing value plus 203.1 has to add up to 339.4. All right. And then the mean square, to get the mean squares, you divide by your degrees of freedom on that row, and then the f value, mean squared for model divided by mean squared error. Right? I gave you the p-values so we didn't have to have you look things up in a table or use your calculators. Then root mean squared error. I was surprised how many people there were that got this right, but then didn't really know what that meant. Right? It just means here's mean square error. So whatever number's sitting there, the square root of that. Right? And that's your SE. S sub E. Right? And then R square, that one, You just had to remember what two things to divide. So what do you divide? Sum of squares for
SSM, isn't it?
yep. So SSM over SST. Right? So the right answer there was 0.4016, which tells us 40% of the variability in number of tornadoes can be explained by the year. Which tells you 60% is not explained, which says there's a lot of scatter around the line. But it is statistically significant. So then standard error of B1, I had you compute that. The standard error of the slope is SE over the square root of n minus 1 times SX. Right? So root mean squared error on the top, SX, which is up here in this table. IQ is X, so standard deviation of X is 13.17. That's going to go in there where SX is, and you have the standard error. Then you divide parameter estimate by standard error to get the t statistic that's missing. And I filled in the p-value for you, so you didn't have to look it up. And that was highly significant. Right? So part B, it asks for the null hypothesis, and then the conclusion. The null hypothesis is that beta 1 is 0, and the alternative is beta 1 is not equal to 0. Most of you wrote it out in words, which is fine. You wrote null hypothesis, there's no association between these two variables. And that's typically how we write the chi-square null and alternative, but it applies here as well. But and then predicted value, just plug in to the regression equation. Both parameter estimates are given to you, so you can just plug that in. I did want to talk about the very last question. Because there are only a few people, probably 4 out of 12 people that understood exactly what I was getting at there. So I graded that pretty lenient also. But explain what the shaded bands are and the dotted lines. The shaded bands are confidence interval for the mean predicted value. Most people got that. Dotted lines are prediction interval. And I didn't take off. Several people used the term confidence interval, but then they said it correct, that it's a confidence interval for a future observation. But actually, we don't call it a confidence interval, we call it a prediction interval, just so you can keep it straight what you're talking about. Right? But I didn't take off for that. But then it says 4 out of 78 points fall outside the dotted lines. So that's these 3 right down here, and this one is just barely outside right up there. All right? 4 out of 78 is 0.0513. So roughly 5% of the points fell outside the dotted line. What's the definition of prediction interval? 95% of the predicted, or not predicted value, 95% of the population should fall within those prediction intervals. That's exactly what we got. So my thought was, no, it's not a concern. I expect to get about 4 of them out. Right? So that's not an issue. Emily, I gave her full credit because she had a good argument. She said, yeah, it's a concern because look at this is a violation of variability, right? Homogeneity of variance. In the middle, you get this huge spread, and that's just the way the data fell. So I went ahead and gave full credit. But I will caution you and anybody else that don't ever make a decision about non-constant variance based on just 1 or 2 points. This is 3 points, but if those 3 points weren't there, it looks really good. So it's just a few points that are causing this problem. And so then you kind of chalk it up as being outliers and don't get too concerned about it. Now, if I only had 20 observations and 3 of them were, then I'd be concerned. But with 78 observations and only 3 down there, then, and only 1 of them that's really, or 2 of them that are really far out there. So, but when I grade things. If you give me an argument for why you answered the way you did, I may not completely agree with your conclusion, but it's a good argument. You understand what's going on, you get credit. Right? One of the running jokes is that if you get 3 different statisticians to analyze the same data set, you'll get 3 different results. So, and then they just argue who's right. So, it's always me. Okay. That didn't work because I need to do that, right? And clear the annotations. There we go. Okay, so now let's get back into chapter 11. And I have just a couple more things to say, and then we're going to start doing the section 11.2, which is a case study. They have a data set that we started to take a look at last time, but we ran out of time. Remember a multiple regression model. How come that's not doing anything? Because what?
It's open. Like, this is on the top. Like, you're in.
Okay, so I need to get back to the page browser, right?
So, top left.
Top left right there. And view. Flip charts. Ta-da! Now, I want the page browser back.
The next one over.
That one?
It should be, or it might be on the left.
Let's try that again.
No, it's the one, I think it's the one with the tools, actually.
That one?
No, just kidding.
Do you see why I struggle with this?
Where did it go?
It closed.
It literally closed.
Okay.
On these. That's not what that button should do.
This makes for a good video when they're staring at the back of my head, watching me try to figure out how to do this.
You may have to click that thing in the center. I don't know what it is.
I don't either.
That's what I told you to do. So that you
Probably click the right one.
I'll tell you what.
Yeah. So I think it's allowing you to like take a picture. So I think if you click the one that's just to the right, up one. Yeah, up right there.
Way to go. Now I want the page browser back, though. How do I get that back?
There's one of those 4, so it's maybe the one you haven't pushed yet.
That's the desktop. That's switch profile. It must be in here. Browsers. There it is. Okay. So I like to have that one. Okay, so back to what we were doing. Multiple regression model. I took the hat off the Y, but beta 0 plus beta 1 x1 I plus ... Remember I had this on the board last time. Okay? So you've got multiple x variables, and the standard notation here is that the first subscript on the x is which x variable it is. So the first x variable, second x variable, the pth x variable.
That's x0 or b or beta is 0, right?
Yeah. If you write too fast with this, it doesn't catch all your movement. Okay, now, I think I didn't get this said last time. What would the interpretation of beta 1 be? After you fit the model, you get your little b's as estimates of the betas, right? What's the interpretation? What does that number mean? B1. It's an estimate of beta 1, but how do you interpret the value?
The impact versus x variable will have on the slope of your model.
Okay.
While holding everything else constant.
That's what I want to make sure, because I don't think I said that before, and since you already had regression, you knew the answer to that. But beta 1, all of the betas are the rate of change So rates, I'll write it this way. Betas are rates of change of y per unit change in x I'll put a subscript of j. So beta j. And then you got xj. So the same x, the beta that goes with that x. Everybody understand what I'm trying to say here? Change in xj while holding other x's constant. So when you say per unit change in xj, that's saying, okay, well, the example we're going to do here in a minute had the 6 variables: high school math, high school science, high school English, and then SAT on those things. Right? Remember that? So the beta coefficient for high school math is the rate of change of GPA, which was the y variable, per unit change in your high school math for everyone where the other variables stay constant. Right? So you can't go changing them at the same time. Any questions on that? Does that make sense? Okay. All right. So we talked about the ANOVA table. And it's the same setup that you had in simple linear regression with one variable, right? So I'm not going to copy the whole thing down there again, but the F test, I think I might have given you this. What is the null hypothesis for the F test at the top, right? The F statistic is mean square for model divided by mean square error. And it's got how many degrees of freedom in the numerator? P. And in the denominator? N minus P plus 1, or you can do N minus quantity P minus 1, right?
That should be minus 1. You're right that way, right? You need to put a parentheses.
Right.
Minus.
No, I thought I had it right, but I was distributing the minus sign, and then I didn't do 7th grade algebra correctly. Okay, so it should have the parentheses around there. Okay, so this is the distribution of the test statistic. It'll be F with these degrees of freedom. What's the null hypothesis?
The model does not help predict.
Okay, in words, the model does not help predict Y. The alternative?
At least
It does.
It does help predict Y, which means, in terms of the individual X's, write it in symbols instead of words. What's the null hypothesis?
Beta 1 equals beta 2 equals beta whatever.
Good.
way.
So beta 1 equal beta 2 equal beta ... beta P all equal 0. And the alternative is at least one of them doesn't. So a really common misinterpretation of multiple regression, people will run it on their software and they look at that F statistic and it's got a really small p-value, like negative or less than 0.001. And they go, oh, wow. So these X variables are good at predicting Y. And they think all of the X variables are good. But it doesn't say that. It says at least one of them is good. It may only be one. You don't know. So then you go to the bottom part of the model, or of the output. No, this is not the collinearity thing. In the bottom part of the ANOVA, you have the parameter estimate, right? And and then a standard error. And so you'll have a line for each of your x variables. They won't be, unless your data set happens to use these as variable names, it'll have whatever the variable name is. So for our example we're going to do, it'll have HSS for high school science, HSM, right? So it'll have a row for each of the x variables. Then it'll have an estimate. It'll be some number sitting there. And then it'll have a standard error of that estimate. Now, did we talk about the formula for the standard error? Kind of a trick question. All I would have said about it is, these are complicated. They deal with matrix algebra, so we're just going to let the software tell us what they are.
Yeah, you did say that.
All right. So now, what's the t statistic?
It's the estimate divided by the standard error.
Estimate divided by standard error, or b sub j for the jth one over the standard error of b sub j. What's the null hypothesis for each of those? You're going to get a p-value for every x variable. What's the null hypothesis of that?
That it equals 0.
What equals 0?
That the beta j equals
Good. The null hypothesis for each of these is beta j equals 0. The alternative is that it's not equal to 0. They're all two-tailed tests. If you want to do a one-tailed test, you can, but you have to form it yourself. Basically, you just cut the p-value in half. Right? But, so this F statistic has beta 1 equal beta 2 equal beta 3, dot, 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 all equal 0. And then down here, it's each one of them separately equals 0. So once you decide, yeah, at least one is a good predictor, you can come down here to try to figure out, well, which one is it? And it might be all of them. It might be, all but one of them. Who knows? But you can check it. Right? Okay, so how would you get confidence intervals for those beta parameters? Exactly. Yeah. And what is that? Same way every other confidence interval?
You have the parameter estimate plus or minus the t critical value times the standard error.
Exactly. So you take whatever your point estimate is of that beta, add and subtract a critical value times the standard error. So in this case, the critical value will be t. So this will be bj plus or minus t times standard error. Now I wrote that in the middle of this table, but it doesn't go under there. It goes over here. But, right? So that's inference on the beta parameters. The inference on predicted values and mean predicted values, same as it was before. Only the formula for computing those standard errors is now much more complicated, and it has to do with matrix algebra and all that. So again, they're just going to give us that. They're going to say, the standard error for an individual predicted value is this number. Now give me a prediction interval. So then you just take your predicted value plus or minus a critical value times whatever number they give you. They make it easy. Question?
Is that formula right there, is that SE sub B sub J, or is that the SE as a function of B sub J, like over there?
It's of BJ.
Okay. Thank you.
Right? Okay? So I think probably we are ready to before I'm going to go to Excel and to SAS, but I do want to point out that R squared is the same as what you're used to, and it has exactly the same meaning, only now it's interpreted in terms of all of the x's together. So what is the formula for R squared? Okay, so sum of squares model over sum of squares total. And it gives you percent of variability in the y explained by the model. Before, we always said percent of variability in y explained by the x variable. Well, now it's the model, meaning all the x variables together. Right? So percent variation in y explained by the model. So all x's. Okay? So what I have here is SAS Enterprise Guide, and I've loaded the data out of the spreadsheet. So you already know how to do all that. And we've got GPA as the y variable, and then the 6 variables that we started talking about. So HSM is high school math, high school science, high school English, SAT math, SAT critical reading. I had to look that up. Couldn't remember what CR was. Critical reading. So basically it's English. And then SAT writing. Right? So there's a writing and critical reading. There is no science part in this data set. So the author then makes the point in this case study that before you ever just start throwing a multiple regression analysis at a data set, you really need to get to the point where you understand the data and you've figured out if there's any problems with the data. Right? So you should look at each of these variables one at a time. Look at GPA. See what the mean is. See what the standard deviation is. See if there's outliers. See if there's missing values or messy data. Right? And do the same thing with all that. So that, I'm not going to go into that much. It's in the book. But then he talks about what's called a correlation matrix. Ooh, what's that? What's a correlation matrix?
A matrix of R's.
Okay, a matrix of R's, a matrix of correlations. And it looks like this. When you have SAS do it, your output looks like that. I don't know that I can zoom this up. And I ran out of time. I was trying to copy and paste this into an image file where I could zoom it up. But can you read those numbers?
Did you try control on the keyboard?
Yes, I did. It didn't work. So I'll just read some of the numbers. But it's a matrix. So it has a row for each variable, including the y variable, and a column for each variable. And then on the diagonals is the number 1. Because anything correlated with itself, it has a correlation 1. Right? Makes sense? So then across the top row, this is GPS correlated with high school math. It has a value of 0.4197. So around 0.42. High school science is 0.44. High school English is 0.36, and so on. Underneath those are p-values. And notice that at least in this top row, which is the y variable GPA, all of those p-values are statistically significant. They're less than alpha equal 0.05. Way less. What's the null hypothesis? I love it when you have p-values, but you're not sure what it's testing. What would the null hypothesis be? No correlation, right? That there's no correlation. So remember, we use R's for the sample correlation. We use rows for the population correlation. So this says the population correlation of GPA with high school math is not 0. It doesn't mean it's particularly strong. It just means, well, it isn't 0. So that's not always that helpful. But you can look at a correlation matrix and figure out not only what's correlated highest with your y variable, but also look at your x variables and see how they're correlated. So if you look into the body of the matrix, you'll see probably the highest one that I notice is down here, 0.73, which is SAT writing with SAT critical reading. I guess that makes sense, but they're pretty highly correlated. So what happens in a multiple regression model, if you have two variables that are highly correlated, each variable, those T statistics that I talked about, each of those T tests are what we call variables added last tests. What? What does that mean? Variables added last. Well, it's after you've explained all the variability in Y you can with all the other X's, what does this X explain? Right? So, if it's added last to the model, does it explain any remaining variability? Right? So, if two things are highly correlated, once one of them's in the model, the other one might not have that much left to explain, because everything it could explain has already been explained by a different variable. So sometimes variables in a multiple regression model will show up not significant just because there's another variable in there that it's closely related to. Right? So figuring out the best model is a bit of an art form. Okay? So now they talk about a scatter plot matrix. And this is so easy now. It used to be really hard to program this. I don't know how to find it. That's not what I want. I've already run it, so it's in the background here somewhere.
There's a thing on the top left that says scatter plot matrix.
Where are you seeing that? I was looking.
In the project tree.
Oh, here. Yeah, I wasn't even looking. There. I knew I had it. So this is the same idea as that correlation matrix, only it's a scatter plot instead of a correlation coefficient. This is really useful. You can look at each variable as it relates to GPA. What do you think when you look at that line?
It looks cool.
It looks cool, but do any of them...
Like shotguns, those look really interesting.
Well, why are these vertical bars like that?
Because there's only certain numbers.
And that's called discrete, right? So that's a discrete variable. There's only certain numbers. So it's on a scale of 1 to 10, and there's no decimals. It's 1, 2, 3. And so that's a summary. Like an A is a 10, an A minus is a 9, a B plus is an 8, and so on.
Aren't technically all of these discrete, but the other ones has 600?
Well, yeah, your SAT scores aren't going to have decimals on them, so technically, but when the range is so big, you can treat it as continuous. But again, these kind of look like shotgun blast, but it's hard to see individual points. There may be a cluster of points kind of in the middle, but the correlations, remember, were like around 0.4, which is pretty weak correlation. It was statistically significant because, well, it didn't zero, but... So you use a scatter plot matrix like this to try to figure out, well, which variables look to be the most promising to try to predict GPA in college. All right. Okay, so I got to quit there. We'll pick up from here and we'll actually run the model next time. We'll do it both in Excel and in SAS, and then we'll start interpreting those beta coefficients. All right, we will see you Wednesday.